Right, you are cordially welcome once again to our next lecture. My name once again is Dr. Hinyasari. I am ready to walk you through the journey, through the valley of the shadows of research methods. And I'm ready. I don't know about you, but I'm wholly ready. Today I want to look at section 4. Section 4 is on parametric hypothesis. You might remember that the last one we did was parametric hypothesis, but it was on one sample. You remember? We had one sample and then we look at the one sample. Today we are going to do two samples. So let's look at the overview. It's section 4 overview. We are going to extend the one sample this time to a two sample study where the difference between the two population mean is important. So we have two samples, but the focus is on the means of the samples. I'll give you an example. For example, we may want to test for the effect of customer training workshop on the sales of salespersons in a company. Or you want to look at even the impact of reforms, of sales in an industry. What is the impact of the structural adjustment program on the banking industry before and after, sort of? Okay. So before, maybe the overall performance was about 80%. Then you brought that reform. Then the overall performance became what? 89%. You might surely want to attribute that rise to what? To the reforms that you brought into the picture. And that is what we want to look at. Then from that you can make policy prescriptions to the industry. So this is not no joke. This is a real deal that happens in real matter systems, which we want to look at. So these are the topics. Okay? Hypothesis on differences between two means. We shall also look at hypothesis on differences between two means using independent samples. And then we have one which is using dependent samples. Dependent samples, you might remember, is also called paired data. And then finally we can conclude. So that's the general overview. The reading list is still there. You might want to continue to look at them and then see. Each reading list will have a different chapter and page for the course that we are. So we are ready to swing into the whole job of hypothesis testing. Now let's see this chart. Very mumbo jumbo, very complex in that form. But watch the line of movement that we want to go for. We want to go through this line of movement because this one is single sample. So we want to go through this part of two samples. And then when we go through two samples, we now do not want to look at independent. We rather want to look at dependent, which is also called paired. So the samples are together, paired. Now paired, you will understand later that paired is dealing with this subject before and the same subject after. Okay. So for example, you look at the ages of men before 2015 and then the ages of men after 2015. Or you want to look at the performance of level 300 students before IA and then the performance of level 300 students after IA. You see, in this case, you still have the same level 300 students repeating themselves. So sometimes we call them even repeated samples, dependent samples. But then while you look at the performance of level 300 students in main campus, okay, and then compare that with performance of level 300 students in city campus, that is independent samples. You get a point? Excellent. So the test we are going to be using will be that, and the sample we are going to assume is small sample size. So we are going to assume that the sample size is small, it's not large, and so we are going to be using t-test and not z-test. What a joy! What a way to start the entire caboodle. Okay, so let's get deeper. Along this line of parametric and non-parametric tests, you can see that our focus is going to be on the paired t-test, and we call it dependent. Of course, it's got its non-parametric version. The non-parametric version of the paired t-test is the Wilcoxon signed rank test. I won't do that, okay? But you attempt that later when you grow old, okay? But for now, we want to look at the paired t-test, the dependent sample. Let's get a bit excited about it and let's get deeper. So this is a paired sample. It's also called dependent, remember the name. It's also called repeated sample. It is used to test for the differences between population means using two related or paired or matched or before and after samples. So the subjects are repeating themselves. Jolly good. Now, we will look at what we mean by population difference. Because we are talking about this sample and this sample, we have to mention the mean difference. In other words, the difference in the mean between the two samples. And that mean difference is called mu d. So whenever you see mu d, it is looking at the difference between the two samples. That is mu1 minus mu2. This is the mu d. We shall understand that. And for this topic, we want to remember that the difference between the pairs are normally distributed. So the data is assumed to be normally distributed. It's not skewed to the right or skewed to the left. No. It's normally distributed, which means that it's bell-shaped, isn't it? Wonderful. Now, the difficult area slightly with this one is how to write the hypothesis. You remember when we were doing the one sample hypothesis, it was quite difficult for people to write at least, at most, and all those things. Well, this is two sample. It's two sample. Even the one sample, some were looking at, I'm suffering and all that. But this one is two samples. So let's see how we can write the hypothesis. What's the hypothesis? The first one. This one is saying that the null hypothesis is saying that the difference is equal to 0. So if you have the sample mean for the ages of men, for example, and then the sample mean for the ages of women, what this one is saying is that the mean of the ages of men and the mean of the ages of women are equal. And if they are equal, then the difference is what? Is 0. So if the mean is 50 here, the mean is 50 here, then the difference is 0. So the mu difference is now 0. What is going to be the opposite? The opposite will obviously be what? That the mean difference is what? Is not equal to 0. And the fact that we have equality and not equality clearly shows that this is what? A two-sided hypothesis or two-tailed test. Now that one is cool. That one is fine. Okay. But then the one-tail are not small boys. Okay. The one-tail are in such a way that, look at this one. The mu difference is less than or equal to 0. Now, if you have the mu difference is less than or equal to 0, what that means is that if you have mu1 minus mu2, it is less than or equal to 0. And that would mean that one is greater than or equal to the other one. Okay, so let's get it clear. So if I have the mean age of men to be 40, and then you have the mean age of women to be 50, for example, then you are going to say that the mu age of men is less than the mu age of women. You agree with that? Which is going to take this sign. It's less than. You put a less than down. But then you know that the opposite of less than is what? Greater or equal to. And so clearly, if this one is less than, then the opposite is going to be greater or equal to. Which of course, as you know from today, that is what we call what? The null hypothesis. Because the null hypothesis has got some level of what? Equality within that. An example will do. An example. Because this is looking like Hebrew, isn't it? Let's get deeper and let's look at an example. Before we come back to an example, let's remember the steps in hypothesis testing. Do you remember that we said that the first thing you do is to formulate your null and alternative hypothesis? The second is to do what? Who can remind us? The second step, after indicating your null and the alternative hypothesis, who can remind us?
You find your T calculated and your T tabulated.
Excellent. You find your T calculated. Excellent. And then you find your T tabulated. And then you do what? You compare them. And when you compare them, you remember the dancing rule. Okay, if the calculated is greater than the tabulated, you do what? Somebody say you reject. You reject. I remember. Did I tell you the story where the students were dancing when they were entering the class? Calculated greater than tabulated, reject. But that is good because that is the only way probably you have to remember. Okay. Now the calculated is this one. Remember, this is a two-tailed test, and so the calculated is not a small boy, once again. Remember the other one, the calculated was quite easy. Look at this one. It's D bar. Anytime you have a bar on top of something, it's telling you that is what? Something bar. Anybody going to give me that? Something bar. If you have a bar in front of anything, it's telling you, yes, Dorothy. Whoa, Dorothy, yes. Whoa, Dorothy. Yes, Dorothy.
The mean of what you are looking for.
Exactly. The mean. So it tells you that this is the mean. But we are looking at difference, isn't it? So it's not just the mean, but it's the mean what? Difference. So the first thing you will notice that the D bar is the mean of the sample difference. So before you can get the D bar, first get the difference. So you look at the values for the first sample, and then the values for the second sample. Then for each observation, you subtract the first from the second, the after minus the before. So if the before was 2 and the after is 5, the difference is going to be 5 minus 2. Then the first difference will be what? Positive. But sometimes the before will be what? Maybe 4. Then the after may be, say, 3. You still do after minus what? Before, which gives us what? Negative 1. In that case. So some of the differences will be negative, some of them will be positive. No problem with that. Then you will find the mean of that, which means that you have to add all of them, which is a summation sign, and then divide it by the total sample, and that gives you the difference. That should be the top part of the T calculated. Then the down part is the standard deviation. That one is megamama. Is a megamama formula there. The standard deviation of the difference. How do you compute that? You're going to see that very soon. But before then, note that the sample size is n. So the standard deviation divided by the square root of n is this bottom one. But let's get deeper into the standard deviation, because that one is not a small girl at all. Look. Before that, before we dig deeper into that, in fact, let me document that for you to have a look. Let me document that for you to have a look at her. Okay, let me document that. You have the mean to the D bar, which we said is a summation of each individual difference, okay, divided by the sample size. This is a difference. This is a difference between the mean. And then, so this requires that you first of all find the difference for each one, and then you divide it by that. Now you go to the standard deviation. The standard deviation is a very, very long formula. Okay. So, in fact, let me get back here first and I pinpoint it, because sometimes some of these formulas could be very, very strange. Okay, so that you can sense it. Let me come back here and then show you that before I move on. It says that the difference minus the mean difference, all squared after you sum them, divided by the degrees of freedom. You know the degrees of freedom is always n minus 1, n minus 1. Okay. So the difference. So this requires that first you need to know the difference for each guy. Then you subtract it from the mean difference. When you finish, sum it. When you sum it. But before you sum it, you make sure that you square it first. Okay. You square it first before you sum. Sometimes people make mistake, they don't square it. We shall look at an example very soon. So let me go back there, okay, and document that here. So, and some people will forget bringing the square roots. You have to bring the square root, okay. Bring the summation sign, difference minus the mean difference bar, okay, which is the mean difference. You square it, divided by n minus 1, which is your standard deviation. And this is the whole job. This is the grandpa of the whole topic that you want to look at. So these are the key important things you need to note about the calculated. Now we are going to get an example right here. Let's remember our decision rule again, in case you have forgotten. Reject if the calculated is greater than tabulated. You remember it still stands. Reject if the p-value is less than alpha. You also remember that. Who can remind us what the p-value was in simple language and what the alpha was? Who can remind us? Who can remind us? Who can remind us? Who can remind us? Have you eaten? Have you eaten? You have to eat. Then you can remember. Yeah, Marilyn.
The p-value is the actual mistake you're expected to make.
Yes.
And then the alpha is the expected mistake.
Good. So which one do you want to be smaller?
You would want the actual to be smaller than the expected.
There you go. I don't know how you got it, but you got it. Okay? Once you got it, that's it. So you want to make a smaller mistake. When you make a smaller mistake, then you will have enough what? Confidence to be able to reject the null hypothesis. So if you reject the null hypothesis, there must be a significant difference. Because the null is saying that there is no what? Difference. You remember? But you are rejecting that. So you're actually saying that there is a significant difference between the mean of this sample and then the mean of that sample. That's the point. And that's what we want to look at. So let's get this example. You are going to get your hands dirty. It's up to you to get your hands dirty. Let's assume you are the boss of your company and you got some salespersons. Some of them are ticoliko. They are not really thinking straight. Some of them are messing about. There's so much complaints about some of them. And so you decide to send some of them for a training workshop, hoping that the training will have some impact on the customer complaints. So they don't, I don't know, but it's a problem in Africa where you don't have a lot of people serving well. So customer training is a very good thing. So you send them for this training workshop, and the question you are being asked is whether the training had made any difference in the number of complaints. And you collect the following data. Okay, watch the data with all your beaming eyes. The training. Now, how would you know whether the training had made a difference? How would you know, using the number of complaints, whether the training made a difference on any person? How would you know that this training made a difference? What would tell you, as far as the number of complaints is concerned, for you to know whether the training made a difference? See, some of you have made your face like that.
The difference between the number of complaints before and after the training.
Okay, what would you expect?
You expect that after the training, the number of complaints will reduce.
Exactly. That was easy. So if the number of complaints is smaller, then it means that the guy had benefited, isn't it, from the training exercise. So here we go. I'm going to ask you a question. So look at it with all your beaming eyes, because I'm going to ask you, who must have benefited the most from the training? So here you have CB. Before, the complaint was 6. After, complaint is 4. TS. Before, complaint is 20. After, complaint is 6. And then last guy, MO. Before, 4 complaints. After, 0. Now let me ask you, which of these 5 guys must have benefited the most from the training exercise? Think deep before you speak. So think deep, or taste not this experience spring right here. Who will set the ball rolling? Who will set the ball? Who do you think must have benefited the most from this exercise?
I think TF has benefited more, because when you look at the difference in the number of complaints after the training compared to that of before the training, you see that there is a wide difference between the number of complaints.
There's a wide difference. Who has a different idea? Me, I like different ideas, so I like different. Marilyn, you want to go for that?
Yes, I think it should be MO, because I mean they all had the same training, and he got zero number of complaints after the training, which means it really impacted on him.
I like that. I like it. You see, it's getting exciting, isn't it? Who has a different one? What's a different one? I mean, the rest of you might probably want to either support one of them, but of course, one of them is wrong, isn't it? And one of them is right. Who is right? Now watch something, and I understand where you're all coming from, because anybody who is watching this will probably agree with you. You look at TF. TF had 20 complaints, has cut it down all the way to what? 6. MO had 4, has cut it down to nothing. Which of these two guys do you think benefited the most? Now you are getting the picture. Now, for every complaint that MO will reduce, TF will reduce it by how many times? 4 times. So for every one complaint reduction that MO will have, TF is reducing the complaint 4 times. Do you realize that? Yeah. So now you can sense who is benefiting most. Who is benefiting? That's it. TF is a guy in the wearing ring. So he is the one who must have benefited the most from this training exercise. Okay. Of course, we know that MO has got 0, but we will not be deceived by the 0 factor. Because in terms of relativity, you can sense clearly that TF is really benefiting from the whole exercise. Now, who must have benefited the least from the training exercise? Now, look deep. Look deep. The answer is there. Easy peasy. Who must have benefited the least? Before you actually answer, remember to drink saliva. You want to go for it, Dorothy?
I think RK didn't benefit most from the training because
Why?
before the training he had no complaint, and after the training he still had no complaint. So it might have been that he didn't even listen. So he had no.
That's it. Perfecto. Because do you even think RK should have been taken to the program? There you go. The guy shouldn't have gone. He's only wasted the money, okay, of the whole company. He's going to just eat, chop, and sleep at the whole workshop. He just wasted that. So he benefited the least from the training exercise. So these are the preliminary guide. So now, let me ask you, just from hindsight, from judgment, you've got experience in looking at this. From experience, on average, do you think the training must have done them good? On average. Yes or no? Yes or no? Yes or no?
I think they really benefited from the training.
Perfect. Now, I like that answer. Let's see whether we can put this to statistical word fire. Okay. So don't forget the answer you are giving now. On average, we think that they've benefited from the training exercise. Now we are going to check statistically whether they've benefited. So the first thing we want to do is to do some few things here. Let's start. We want to now create differences. So we're going to create some columns. The first column we are going to create is column D, which is going to be the difference for each guy. When we finish, we will create another column which is known as D minus D bar. Alright? Then when we finish, we will get another column which is D minus D bar, or what? Square. So we have this one, we have the next one, we have the next one. And we are going to find it. So let's remember the values now. Let's go back to the preamble. And let's remember the values. Remember, it is going to be after minus what? Before. So the first difference value is going to be what? 4 minus 6. So the answer is what? Negative 2. The next one will be what? Negative 14. The next one? Negative 1. The next one? 0. And the final one? Negative 4. I thought somebody was going to say 4. Good. So let's keep those values there. Okay. So the first one you said was negative 2. The next one was negative 14. The next one was what? Negative 1. Then you have 0. Then negative 4. Isn't it? Now we have to find the mean, don't we? We need to find the mean of these values. I want you to find the mean for me. And tell me, you raise your hand and then tell me the value of the mean. Who is ready to mention the mean? The mean. Take a calculator and make sure that you are trying to get the mean.
Negative 4.2.
I like that. I like the way you said the negative 4.2. Because someone will first start by positive 4.2, isn't it? So it's very important you apply the negativity. You get a point. If you don't apply the negativity, everything is going to go down the drain. So it's very important you apply the negativity right there and there. So we have the mean to be, let me put that somewhere here. Mean to be d bar negative 4.2. Negative 4.2. Now in our next column, we are going to create that column, can't we? So we are going to have, and watch this carefully because this could be quite tricky. Because the rule is saying that the individual observation difference minus the mean difference. And the mean difference is already what? Negative. And there is another what? Negative. So when you have negative, you should check that it's going to be what? Positive. Okay. So the first one is going to be negative 2 minus 4.2. Isn't it? Then the next one will be negative 14 minus 4.2. Now negative 2 minus, which is plus 4.2. That will give us what? 2.2 positive. Negative 14 minus 4.2 or negative 14 plus 4.2. That is what? Negative 9.8. Excellent. Then you have negative 1 minus 4.2. That is what? 3.2 positive. Then the next one obviously is going to be 4.2 because it's going to be 0 minus 4.2. And then the last one will be what? 0.2. Wonderful. What a joy. What a joy, the way to go about it. You see, this thing is very easy peasy, isn't it? But when you're in an exam room, it's a different ball game, isn't it? When your eyes are looking like blues and you see everything in stars, you know. So you have to take your time and respect it. If you respect it, it will respect you. Now that you've got these values, what you have to now do is to take the square of each one of them. The square of each one of them. So you square each one by one. 2.2 squared. What is that? So that gives you 4.84. Then you have negative 9.8 squared. That, of course, is going to be positive, isn't it? Positive. So you don't even have to type negative on your calculator if you know it. But if you don't know it, please just type it. You don't want any wahala. Just type it. So you have 9.8 squared. That gives you what? 96.04. And then you can continue and continue and continue. Now, when you finish all of them, what you are going to do is to add them, isn't it? And that will give you the top part of the formula. Okay. I don't want to go through all these. Now, I have done them. Let's see how they look like. They look beautiful. Okay. They look like beautiful. Let me just come here. So let's see. So here you have all the values we were mentioning. I've deliberately made some few changes here so that when students are actually writing it, they will not think that this is it, because I've deliberately made some errors here. But at the end of the day, the values you will have on the d bar square will be the same. But watch, the values you will have here will not necessarily be the one you had. If you can remember, the values in the d minus d bar column are slightly different from the one we had. If you check it carefully. For example, some of them, like this one, like this, was in minus, but I have deliberately put it as 9.8 so that you can work this yourself and then come out with exact values. But of course, the values on the far right side, which is the d minus d bar square, are all exactly the same. When you add all these values, that should give you 128.8. Okay, 128.8. Let's go back to our formula. Check the formula. That becomes the top part of this standard deviation formula. Okay, and then of course you have n minus 1. In this sample, n is what? 5. And so n minus 1 is what? 4. So you are now going to divide 128.8 by n minus 1 or by 4. And when you do that, and then you take the square root of that, oh, this is what you get. You get a beautiful value, which is 5.67. Our standard deviation, without a shadow of doubt, yeah? See the way I'm dancing with the doubt, is 5.6. You see, when you're in an exam and you are trying to work days and you know what you are doing and it's all smooth sailing and it's all nicely moving and you get the value, then you look at the value and you smile at the value and you say, wow, you see how I put you to justice. But when you are struggling, you just look at the value and start canceling it and you call for more papers unnecessarily, you start getting confused. But when you get it like that, 5.67, wow, then you are so glad, you are joyous, and you are good to go. Now that you got this value, the rest is just easy peasy. Let's go back to the value, the T statistic. Watch it. The most difficult one is what we have put justice to, SD. The rest are just easy peasy. The D bar, we know what it is. The standard deviation, we now know what it is. The D bar is still negative 4.2. The N, we know what it is. So we can now start our entire analysis. So we are going to go to the beginning to start the start. The beginning thing you want to do is to be able to learn how to formulate the hypothesis. So go back to the story and tell me, what sign are we going to use to formulate this hypothesis? What sign? Anybody? What sign is guiding us to formulate the hypothesis? What sign is it? Mathematical sign. Vera, you want to go for that?
I think it's less than.
So the sign is less than, and then the opposite is?
Greater than or equal to.
Greater than or equal to. Okay, any other? I'm not saying she's wrong or she's right. I'm just saying any other. So yours might be wrong or right. Yes, Daniel.
The sign should be equal to or not equal to because of the word difference.
Because of the word difference. Okay. Now let's analyze it too. I know where Vera is coming from when you say that you think it's going to be greater than. Because you see, in her mind, when we say something has made a difference, she's looking at it in terms of positivity, isn't it? Made a difference, positivity. But these things, you don't go by how the implication is. You go by the key word that is driving it. Because the positivity could also be negativity. Because the issue about made a difference could be that it came down. So complaint could be worse, isn't it? It could be worse. Maybe this guy who had 20 complaints, tears, will probably go and have more complaints after the whole process. It's so bad. All through. So it is possible for negative things to come. That is why the word is what you look out for. So the key word is what you are looking for, and the word is difference. And we know that the sign for difference is what? Not equal to. And then opposite of that is equal to. So on the basis of that, we come back to our hypothesis. Before, after comes first. So you have after minus what? Before. So I'm going to write the mu for after minus the mu for before, and then say that the difference is what? 0. Okay. So look at it. So the difference is equal to what? 0, which means that there is no difference in the number of complaints, and that implies that the training is what? Is not effective. Does it make sense to you? Which comes back to your point, Vera, that you were making. Okay. Now you realize that the training is bogus because there's no difference. So why did we even go to the training workshop? But if there is a difference, then we can now attribute potentially that difference is what? Is either bad or good. But of course, you would want the difference to be what? To be very good. And the reason why you'd want the difference to be very good is that normally the positivity is in your mind. So the difference is effective, but that is not what you write. So here, the greater than implication is coming here, but that is not what you write. What you write is the actual sign that has been given in the storyline. The training is, look at my way of writing the positive. Remember there's I here. Positive. Okay, it's not positive. But that sounds nice, but it's not positive. Okay. So this is how you write your null and alternative hypothesis. Beautiful. You get 5% for that. Then you go to the calculator. Now we are ready to do a calculated. And you remember that already looking at the formula, we had the mean to be negative 4.2. You remember? And then we had the standard deviation to be 5.67. Now we are ready to take this value divided by that value and then divide all and then get our final value. And the rest is very easy. Let's go here. So you have t equal to d bar. You substitute every value. Minus 4.2 divided by 5.67, also divided by the square root of 5, which is the sample size. Now, please let me tell you the mistake some people could make. On your calculator, they'll rather go and type negative 4.2 divided by 5.65 divided by square root of 5. That is a mistake. Because what the calculator is going to do is that the calculator is going to do negative 4.2 divided by 5.65. You realize that? And then it will use that answer divided by square root of 5, which is wrong. So what you have to do is that on your calculator, you have to type negative 4.2 divided by bracket. You get a point? So that you put the rest in a bracket. So that it will do the bracket first, which is board mass, bracket of division. So brackets will come first. So it will handle the denominator first before you will take the numerator divided by the whole of the denominator. You get in the picture? So it's very important the way you type it so that you get a straight answer. However, some people want to do this denominator first and put it down, isn't it? Those who don't want any wahala in their life, okay? They say, me, I don't want problem. I just want to do 5.67 divided by the square root, put it down. Well, you won't get marks for that. But if that is what will help you to understand, you can do that. And when you do all of those gimmicks, your T calculator will be negative 1.66. Wow, what a job. What a way to start the whole caboodle. I am enjoying this value because this value is not going to be compared with the tabulated, and then we can now make our conclusion. Now we are going to use the value, find the value of the tabulated. Now that we've got our calculated, we need a tabulated. And the tabulated has got a formula. Look at the formula. Okay. In fact, let me go back to our original formula that we know of. Let me go back here. Do you remember the tabulated? It's not changed. The tabulated from sample one sample, it is given by T subscript alpha comma n minus 1. You remember? It's still the same thing. It's not changed. Alpha here was not given, so we'll assume is what value? 5%. So you have T subscript 0.05 comma 5 is the sample size minus 1. That gives us 4. So let's go to our T table. You all have the T table. Pick the T table. And then on your T table, look out at the top. 5%. What tail are we dealing with? One tail or two tail? Two tail. Excellent. So look at the top two tail. Pick 0.05 at the top T tail. Now look at the far left, the degrees of freedom, and look out for 4. And then bring the 4 rightward, bring the 0.05 downward. Where they meet, you tell me the value of the tabulator. What value did you get? I hope you got it. I hope you got it. Anybody want to tell me the value?
The value is 2.776.
Final answer.
Yeah.
Final.
Yes, final.
Yes, you've eaten. Okay, so that is very good. The value is 2.776. So you can see that this is the value that she just told us, 2.776. This is the tabulated. And now you can see that we can compare easily now. If the calculated is greater than tabulated, you reject. So are we going to reject or we are not going to reject? We are not going to reject, isn't it? The absolute value of the calculated is smaller. It's too small. It's smaller than that. So we are not rejecting the null hypothesis at 5% level of significance. But you have to conclude, because doing that doesn't conclude it. So if you are not rejecting the null hypothesis, what are you saying? What are you saying regarding the training? Who can tell me? What are you now saying regarding the training? Has the training made a difference or is not made a difference? Is the training effective or is not effective? This is where thinking and gumption comes to play. Yes, Daniel.
Training has been effective.
Why?
Because we are not rejecting the HO since the T calculated is rather less than the T tabulated.
Good. And then now the null hypothesis said what?
We should reject.
What did the null say? That the training is what?
Is effective.
It's effective or ineffective?
The null is saying there's no difference in complaint, which means it's not effective.
Exactly. So you see, that is why we always have to know what the null means practically. Some people after the last lecture they will say greater than, less than, greater than, less than. It's not about just greater than, less than, but you got to learn how that implies to the storyline. So this one is saying there's no difference, which means that it's not effective. But now you are not rejecting it. Okay, you are holding on to that. Okay, so you are now also saying clearly that there is no what? Effectiveness in the training. So the training is ineffective. It's bogus. Do you remember the answer you gave initially about the training? We all said from hindsight, from hunch experience, that the training was good. On average, we're all saying the training is good. Now you can see that the training is not what? Statistically speaking, the training is not what? Effective. That is why hypothesis testing is very important, because it helps you to get a clearer picture of the whole process. This is known as the critical value approach. But you can also use the p-value approach to make the judgment. So let's look at the conclusion that we just said. Okay, you can use this approach. This is the critical value approach. You can find the whole process also using the p-value approach. Let me just recapitulate, remind you something small that you did last time. Using the p-value approach, we said that for you to reject the null hypothesis, what must be the relationship between the p-value and alpha? P-value must be less than what? Alpha, for you to reject. So we expect our p-value to be small. If you made a smaller mistake, what it means then is that you have enough confidence to reject the null. In this storyline, our alpha is already what? 5%. So we would want the p-value to be smaller than 5% for us to reject the null hypothesis. Let's go and see how to get our p-value. Let's remember small. Our p-value, to get it, you have to pick the calculated, you remember? And then drop it into the what? The swimming pool. The swimming pool of the table. In this storyline, our calculated in absolute terms was 1.66. You remember? 1.66. So let's go down and go and drop that value. This is 1.66. We are going to drop it into the swimming pool. So look at the table, look at yours too, and search for the values or value closest to 1.66. You have to comb, and this is why you got to respect your table. Okay, have you found the two values or one value? Okay, will anybody tell me the value? Who can tell me the value? What A is the value? Who is ready? Who is ready to tell me the value? What do you have?
The value is 2.771 and 2.779.
Okay, what you are doing is that you are finding a different value. We are looking for 1.66, the value closest to 1.6. So we are not dropping the tabulated, we are rather dropping the calculated. So anybody else search for that and tell me? Yes, Dorothy, tell me the value that are closest to the 1.6. Yeah,
1.664 and 1.671.
You all got that? Any difference? I like it. I like it. It's exciting when you are getting different answers. Yes, Clara, tell us. Clara, tell us the value.
It's exactly 1.660.
It's exactly 1.6. You're getting it now. So we don't have to move left, right, center at all. The value is supposed to be 1.660. Sometimes it could be very frustrating finding these values. And you have to comb. Sometimes you have to respectfully comb the whole process. Now let me show you. Let me maximize this one a little bit. Then you have the feel of how sometimes it could be challenging. The value that we are looking for in this storyline is 1.660. What is that? Okay, so the T table that I'm showing here doesn't have all the values at the bottom. Okay, so it's chopped off some of the values. You know what I mean? So, but if you look at the paper there, you will see clearly on the values that it comes at the bottom here, below this, isn't it? 1.660, right down there. Now, that is not your p-value, you know that? If you ever thought that was your p-value, you have to think again. Because that is not your p-value. But that is going to guide you find the p-value. So to get a p-value, you have to look vertically up to pick the p-value at the top, remembering the tail that you are dealing with. What is our p-value now? Everybody? 0.1%, which is 10%. Finally, what a joy. Our p-value happens to be 10%. So p-value here is given by 10%. Of course, you can see clearly that that is bigger than the alpha. Now, we would have rejected it if it was smaller. Now it is bigger. P-value is too big. You see, what this means is that we've made too much mistakes. Too much actual mistakes to the point that we have no gravitas to reject the null hypothesis. We've got to go with it. We've got to go with the null, which is saying that the training is ineffective. There is no difference. Which happens to support what? Our initial critical value approach. Remember, you should get the same conclusion. Finally, we can see that our p-value is indeed greater. So on the basis of that, we are good to conclude. And the conclusion goes somewhere like that. The conclusion is, you see, all those things we are saying, I've written them in the slides for you. Remember, it's a two-tail, the value is 1.660, and p-value is 10%. Has the training made a difference? And the question now is the difference due to chance? So let's first ask, has the training made a difference? We know the answer to that. The training made no difference. I love statistics. I don't know, I love statistics. See, I love it because it tells you clearly that whatever hunch, judgment, experience that you had is irrelevant. Put the thing to statistical fire and let the statistical fire prove us whether the situation is so. So now let me ask you that tricky question. You remember that tricky question I always ask you? Is the difference due to chance? And then somebody say, hey, yeah, I'm dead. Okay. Is the difference due to chance? This is where intelligence comes to play. It requires that you fully understand the entire whole process. Then you can tell. So, is the difference due to chance? What is the difference here? The difference. Are you calculating the difference? Okay. So, let's see the difference. Daniel, what is the difference? Yeah, that's Daniel. Yeah.
Let me calculate it again.
You've calculated? Yeah, what is it?
Let me calculate.
Oh, you want to calculate? Okay. But what minus what are you dealing with?
Minus 4.2 minus 1.66.
Okay. Now, if that is the difference you would have used, then that wouldn't be the difference. And I'll tell you why. Because, you see, the interesting thing about two sample is that two sample is dealing with differences already. So the difference is what you already calculated, the mean difference. That negative 4.2. So in absolute terms, the difference is 4.2. So we don't need to calculate the difference anymore. You got a picture? So there is no difference to calculate except what you've already calculated, the mean difference of 4.2. So now still using that difference of 4.2. Is that difference of 4.2, is it due to chance or is not due to chance? Now this is what intelligence comes to play. Now if you don't know, you just say you don't know. So by force in that regard. Okay. Is it due to chance? But you see, before you say whether it's due to chance, just think about it first. Did we reject or we didn't reject? In this case, we did not reject the null. So we went ahead to say that there was no difference. And we agreed that the training was bogus. Okay. So now we are asking you, is the difference due to chance? Yes, where?
I think it's due to chance. The difference is due to chance because we rejected the null hypothesis. We said that the training was not effective. And so the difference was very significant. That's why we rejected the null hypothesis.
That's it.
Yeah.
That's it. Okay. So we are saying that the training is bogus, isn't it? So if the training is bogus, then what we are actually saying is that the complaints before is not different from the complaints what? After. Is that not what we are saying? So we shouldn't have gone for the training. Right? If there was any difference at all, which in this case was 4.2, if there was any difference at all, then it must have just happened by what? By chance. It wasn't important. In other words, that difference of 4.2 was not significant enough to warrant a rejection of the null hypothesis, which was saying that there is no difference. Okay, so the null was saying that the training is bogus. We've seen that the training is bogus, but there is a difference which somebody you can pick on and say that you can't tell me that this training is bogus because on average we had a difference of 4.2. Well, the conclusion is telling that 4.2 was not too important. It's not too significant for us to warrant a rejection of the null. So if there is any difference at all, it just happened by what? By chance. In other words, as far as we are concerned, the complaint after is more or less the same as the complaint what? Before. That is why the training was bogus. And so if you tell me that there is a difference, then I'm also telling you that difference will just happen by what? By chance. So you're not getting the whole essence of the difference due to chance or it's not due to chance. Sometimes when you ask whether it's a difference due to chance, somebody say, hey, this difference thing or this difference thing again. But now you get the whole picture. No significant difference between the complaint before and after. So we go to the slide. The training we already said was bogus. If there was any difference at all, it was just by chance. Understanding that last principle. You see, he's not a small boy. Exactly. Understanding that last principle is the whole point of the two-sample hypothesis. What a joy! What a way to begin the entire caboodle. Okay. So, ladies and gentlemen, doing two-sample hypothesis, this is the entire conclusion, summary of the whole result, and all that. You can check it later and have a feel of that. That is how you do hypothesis. And this is a two-tailed test. Later on, when you have a one-tailed test, a different ball game comes into the picture. We will learn later how to do this hypothesis testing in our software. Okay, we shall learn that later. But for now, remember that in this very case, the difference was just by chance. So you have some practice questions to go and look at home. And the beauty of this practice question is that I have devised the difference for you. I've calculated the difference for each one for you. Very, very simple. A new therapy has been devised. And you see, that therapy is used to lower blood pressure. People don't like blood pressure. So anytime you have it like that, you have to think about it. Lowering blood pressure, is it positive thing or negative thing? Now that's what it is. The systolic blood pressure of 10 patients were taken before and after completing the course. What course? After taking that therapy. The question is, does the therapy work? It's a short sentence, isn't it? But I know a lot of effort goes into answering that question. That work, that the therapy work is not a small thing to do. You have to use 5% level of significance. This was before the therapy and then after the therapy. You see that the blood pressure was smaller before. Even after, you see the first guy, he's still having higher blood pressure. But that's not the only case. Some of them, their blood pressures were low, higher, and now they reduce after. So the differences are all shown. Some of them are negative, some of them are positive. You have to now check whether the therapy does work. Second one you want to practice. Chia is a VC. I have every right to say Chia because it's written down. It's a VC of a large manufacturing company, and he recently noticed an increase in absenteeism. That he thinks that the absenteeism is related to the general health of employees. That's why they are becoming absent. You see, people are not exercising, so they are becoming absent each week. So 4 years ago, what Chia did was to attempt to improve the situation. So he began a fitness program in which employees will exercise during their lunch hour. There were a lot of ogbolos in the whole company. And to evaluate 4 years down the line, he wants to evaluate the program. So he randomly samples some of the participants and found the number of days each was absent. Now below are the results. I'm going to show you that. At 5% level of significance, the question is, did the program reduce absenteeism? It's not a small question. Or it's like saying that, did the program work at all? But watch something. The word reduce absenteeism and increase absenteeism is a different thing. Absenteeism, you have to ask yourself whether you want to increase it or reduce it. And when you reduce it, is that effectiveness, or when you increase it, is that effectiveness? Those are the questions you want to answer. So you can see employee number 1, before he was 6 times absent, after 5 times absent, after the whole 4 years program. Employee number 8, before was 6 times absent, after rather gone up by 1. So on average, you got to compute the difference one by one and then statistically check whether that is so. So do that with joy. The way to do that is, first, state the null and alternative hypothesis. What is the critical value of the test statistic? What is the value of the test statistic? Decide using the critical value approach. Then find the p-value. And then finally, the most important question, did the fitness program reduce absenteeism at the 5% level of significance? You have to conclude practically. And then, of course, you can answer the last part, which always you got to do is the difference due to chance. Next time I meet you, we shall do session 5. And in that session 5, we shall be learning a non-parametric version of the parametric independent test. Remember to drink deep or taste not the Pyrenean spring. Thank you very much for coming. I wish you all the best. Remember all the time to drink deep or taste not the Pyrenean spring. Thank you for listening to me, and I wish you a happy learning.